All right, welcome back. In this lecture, we review statistical inference procedures for a single population parameter for the situation in which the estimator of the parameter is normally distributed. In particular, we'll review how to test hypotheses about the parameter, as well as how to construct confidence interval estimates of the parameter. We'll do this for two scenarios. First, we'll look at the scenario where the variance of the estimator is known. We'll then look at the more common and more realistic scenario in which the variance of the estimator is unknown. We'll use these procedures early on in the course, and as we progress, we'll generalize these results in ways that will allow us to test more complex hypotheses. So let's get started. So here's an outline of what we'll be covering in this lecture. We'll first look at inferences about a population parameter theta when the standard deviation of theta hat is known, where theta hat is a point estimator of theta. In particular, we'll look at hypothesis tests about theta using z-tests and confidence interval estimates for theta using z-intervals. We'll then look at inference procedures about theta when the standard deviation of theta hat is unknown. In particular, we'll look at hypothesis tests using z-tests and also how to construct confidence interval estimates of theta using t-intervals. So let's look at the underlying framework in which we'll be operating. So let theta hat be an unbiased estimator of a population parameter theta of unknown value. The goal will be to make inferences about the value of the parameter theta based on the estimator theta hat. In order to do this, we're going to need to know something about the sampling distribution of theta hat. Two important characteristics of the sampling distribution of an estimator are its location and its variability. The location of the sampling distribution of theta hat that we'll be using will be the mean, also known as the expected value of the estimator. In general, the mean of the sampling distribution of theta hat will be denoted in a couple of ways in these lectures and notes. First, by mu sub theta hat, which again represents the mean of the sampling distribution of theta hat, and also by this notation where we have a capital E with theta hat in parentheses, and we read that as the expected value of theta hat. So we have two pieces of notation here, but just realize that these represent the same thing, the mean of the sampling distribution of theta hat, which is equal to the expected value of theta hat. Now recall that an estimator theta hat is said to be an unbiased estimator of a quantity theta if the mean of the sampling distribution of theta hat is equal to theta. Under the assumption stated above that theta hat is an unbiased estimator of the parameter theta, it follows that the mean of the sampling distribution of theta hat, mu sub theta hat, is equal to theta. The variability of the sampling distribution of theta hat will be measured using two closely related measures, the variance and the standard deviation. Recall that the standard deviation is the square root of the variance. Now, the variance of the sampling distribution of theta hat will be denoted in a couple of ways in these lectures and notes. First, sigma squared sub theta hat, and also by var for variance with theta hat in parentheses. So again, we have two pieces of notation, but just keep in mind that these represent the same quantity, the variance of the sampling distribution of theta hat. Now the related measure, the standard deviation of theta hat, will be denoted by sigma sub theta hat, as well as by SD for standard deviation with theta hat in parentheses. So again, two pieces of notation that represent the same thing, the standard deviation of the sampling distribution of theta hat. Now, one other term that I want to remind you about, recall that another term for the standard deviation of the sampling distribution of an estimator is called the standard error of the estimator. And so in these lectures and in the notes, sometimes I'll refer to the standard deviation of the sampling distribution of an estimator using that term, that phrase. But I'll also, in some points, refer to that as the standard error of the estimator. So just keep in mind that those terms mean the same thing. And then finally, note that that sigma sub theta hat, which is the standard deviation of the sampling distribution of theta hat, is equal to the square root of sigma squared sub theta hat, which is the variance of theta hat. Now, we will often be working with the standardized version of theta hat, and so we need to know how to calculate it, and we also need to know something about its sampling distribution. So let's start off by defining some notation for the standardized version of theta hat. We'll use uppercase Z with theta hat in the subscript to represent the standardized version of theta hat. Now, what do we mean by standardizing? Well, recall from previous methods courses that a random variable is standardized by subtracting from it the mean of its sampling distribution and dividing the difference by the standard deviation of that difference. Since theta hat is assumed to be an unbiased estimator of the parameter theta, the standardized version of theta hat is given by this expression. So Z sub theta hat equal to theta hat minus theta, that difference over the square root of sigma squared sub theta hat. And that's equal to the difference theta hat minus theta over sigma sub theta hat. Now, recall also that whenever we standardize a random variable, the standardized version of that random variable has a mean of 0 and a variance of 1. And because the variance is 1, the standard deviation is 1 as well. And so that implies that the mean of the sampling distribution of the standardized version of theta hat, which is Z sub theta hat, the mean of the sampling distribution of Z sub theta hat is equal to 0, and its variance and standard deviation are equal to 1. Okay, and then finally, in talking about the framework in which we're operating here, remember that we said that we're going to be looking at these situations where theta hat is normally distributed. And so suppose that theta hat is in fact normally distributed. And so we can express this fact using the abbreviated notation shown here. So theta hat, and then a tilde, and the tilde is an abbreviation for is distributed according to. And then we have the notation for a normal distribution with a mean of mu sub theta hat and a variance of sigma squared sub theta hat. All right, so if theta hat is normally distributed, it follows that the standardized version, Z sub theta hat, is also normally distributed. And because we know that the mean of Z sub theta hat is 0 and the variance of Z sub theta hat is 1, that implies then that the standardized version of theta hat, Z sub theta hat, has a standard normal distribution. This result provides a basis for developing inference procedures about theta when sigma sub theta hat, the standard deviation of theta hat, is known. And so let's take a look at these inference procedures for theta when the standard deviation of theta hat is known. We'll first look at hypothesis tests. So there are going to be 3 types of hypotheses that we can test about theta. Now I've labeled them A, B, and C on this slide. so that we can refer back to them easily by letter when we look at some subsequent slides, for example, when we're looking at rejection criteria. So the first hypothesis test A, is what is called a two-tailed test. The null hypothesis says that theta is equal to some specified value, theta 0. The alternative hypothesis says that theta is not equal to theta 0. Now you'll recall that the null and alternative hypotheses have to be logical complements of each other. They have to be opposites. Okay? And so you can see here that the alternative hypothesis is in fact the logical complement of the null. Now hypothesis test B is what is called a left-tailed test. The null hypothesis is that theta is greater than or equal to some value theta 0, and the alternative hypothesis is the logical complement of that, so it is that theta is less than theta 0. It's a left-tailed test because the inequality points to the left in the alternative, and it has a left-tailed rejection region. And then finally, hypothesis test C is what is called a right-tailed test. So the null hypothesis is that theta is no more than theta 0. In other words, theta is less than or equal to theta 0. And the alternative hypothesis is the logical complement of that. So the alternative hypothesis is that theta is greater than theta 0. The inequality in the alternative points to the right. That induces a right-tailed rejection region, and so that is why it's called a right-tailed test. Now the test statistic that we'll use in performing these tests will be the standardized version of theta hat. And in the context of a hypothesis test, we'll call this a test statistic z-calc. And so z-calc is equal to the difference theta hat minus theta 0, where again theta 0 is the hypothesized value of theta in the null hypothesis. And then we divide that difference by the standard deviation of the difference, which is represented either by the square root of sigma squared sub theta hat or by sigma theta hat. Now, under the assumption of normality of the estimator theta, the reference distribution for this test, in other words, the distribution from which we get our critical points, is the standard normal distribution. And so the rejection criteria provided on this slide provide hypothesis tests with a significance level of alpha. And so for that two-tailed test, we would reject the null hypothesis if our test statistic z-calc is either strictly less than negative z sub alpha over 2, or if the test statistic z-calc is greater than a positive z sub alpha over 2. And I see I have a typo there, so I'll need to fix that. Hypothesis test B, which is a left-tailed test, has a rejection criteria where we reject the null hypothesis if z-calc is strictly less than negative z sub alpha. And then finally, hypothesis test C, which is the right-tailed test. Okay, we're going to reject the null hypothesis if z-calc is greater than z sub alpha. All right, and you'll recall that z sub p is the upper pth percentage point of the standard normal distribution. So z sub alpha is the upper alpha percentage point of the standard normal distribution. Z sub alpha over 2 would be the upper alpha over 2 percentage point of the standard normal distribution. Again, under the assumption of normality of the estimator theta hat, the following formulas give the p-value for each of the three types of hypothesis tests. So for the two-tailed test, the p-value is equal to 2 times the probability that z, where z is a standard normal random variable, 2 times the probability that z is greater than or equal to the absolute value of little z calc, where little z calc is the observed value of the test statistic cap z calc. For the left-tailed test, the p-value is equal to the probability that the standard normal random variable z is less than or equal to the observed value of the test statistic, which is little z calc. And then finally, for the right-tailed test, the p-value is equal to the probability that the standard normal random variable z is greater than or equal to the observed value of the test statistic, little z calc. Now, stating the rejection criteria in terms of p-values, you'll recall that regardless of the type of hypothesis being tested, that is, whether it's a two-tailed test, a left-tailed test, or a right-tailed test, when using the p-value to decide whether or not to reject the null hypothesis, the rule is to reject the null hypothesis if the p-value is less than or equal to the significance level alpha that is being used for the test. That is, and as shown here notationally, reject the null hypothesis whenever the p-value is less than or equal to alpha. All right, now let's look at how to construct confidence intervals for theta. And so we'll first look at how to construct a 1 minus alpha times 100% lower confidence limit for theta. And so again, let z sub theta hat denote the standardized version of theta hat. Then, under the assumption of normality of theta hat, we have the following string of probabilities. So 1 minus alpha is equal to the probability that the standardized version of theta hat, which is z sub theta hat, the probability that that random variable is less than or equal to lowercase z sub alpha, is equal to the probability that theta hat minus theta all over sigma sub theta hat is no more than z sub alpha. And that's equal to the probability that theta is greater than or equal to theta hat minus z sub alpha times sigma sub theta hat. And so that last probability statement, the probability that theta is at least theta hat minus z sub alpha times sigma sub theta hat, that probability is equal to 1 minus alpha. And so that implies then that a 1 minus alpha times 100% lower confidence limit for theta is given by the expression shown here, theta hat, the point estimator, minus z sub alpha times sigma sub theta hat. Next, we'll look at how to construct a 1 minus alpha times 100% upper confidence limit for theta. And to do this, note that 1 minus alpha is equal to the probability that the standardized version of theta hat, which is z sub theta hat, being greater than or equal to negative z sub alpha, again, that probability is equal to 1 minus alpha. We can replace z sub theta hat by what it's defined to be, so theta hat minus theta all over sigma sub theta hat. And then we can rearrange things algebraically inside the parentheses and get the final probability statement on the right-hand side. So the probability that theta is less than or equal to theta hat plus z sub alpha times sigma sub theta hat, that probability is equal to 1 minus alpha. And so that implies that a 1 minus alpha times 100% upper confidence limit for theta is given by theta hat plus z sub alpha times sigma sub theta hat. So the point estimator, theta hat, and then we go to the right, an amount equal to z sub alpha times sigma sub theta hat, and that gives us that 1 minus alpha times 100% upper confidence limit for theta. And then finally, a 1 minus alpha times 100% two-sided confidence interval estimator of theta is obtained by combining lower and upper confidence limits for theta, each at the 1 minus alpha over 2 times 100% confidence levels. So we construct a 1 minus alpha over 2 times 100% lower confidence limit for theta. That's given by theta hat minus z sub alpha over 2 times sigma sub theta hat. And then we also construct a 1 minus alpha over 2 times 100% upper confidence limit for theta. That's given by theta hat plus z sub alpha over 2 times sigma sub theta hat. And when we put those two confidence limits together, we get a 1 minus alpha times 100% two-sided confidence interval estimator of theta. And so combining these three types of confidence intervals, again, a lower confidence limit for theta, an upper confidence limit for theta, and then a two-sided confidence interval estimate of theta given here on this slide. Okay, next, let's look at inference procedures for theta when the standard deviation of theta hat is unknown. And so let's first talk about the studentized version of theta hat rather than the standardized version. And so how do we calculate this? In this section, we consider the more realistic situation in which sigma squared sub theta hat, the variance of the sampling distribution of theta hat, is unknown. Now suppose that we have an estimator of this variance, an estimator of sigma squared sub theta hat, and that the estimator is based on a number of degrees of freedom, which we will denote by df. Now denote by sigma hat squared sub theta hat, the estimator of sigma squared theta hat, and likewise let sigma hat sub theta hat be the square root of the estimator sigma hat squared sub theta hat, so that sigma hat sub theta hat is an estimator of sigma sub theta hat, the standard deviation of the sampling distribution of theta hat. So in other words, we've defined some notation for the estimated variance of theta hat and the estimated standard deviation of theta hat. Now substituting the estimator, sigma hat squared sub theta hat, for the true value sigma squared sub theta hat, all right, in the formula for the standardized version of theta hat gives the studentized version of theta hat. Now we're going to denote this, instead of using z, we'll use t. So capital T sub theta hat is used to represent the studentized version of theta hat, and that's given by the difference theta hat minus theta over the square root of sigma hat squared sub theta hat. All right, and that's equal to the difference theta hat minus theta all over sigma hat sub theta hat. And so we can think of this as just substituting in the estimates, or the estimate of the variance of the sampling distribution of theta hat into the formula for the standardized statistic, but now it's called studentized. Now, what is the sampling distribution of the studentized version of theta hat? Well, if, again, theta hat is itself normally distributed, then the studentized version of theta hat has student's t-distribution with degrees of freedom equal to df, which is, again, is the number of degrees of freedom associated with the estimator sigma hat squared sub theta hat. Now, the studentized version can be used as a basis for developing inference procedures for theta when sigma squared sub theta hat, the variance of the sampling distribution of theta hat, is unknown. So again, let's start by looking at hypothesis test about theta. So the same three types of hypothesis test about theta are available in this scenario as well. So again, we have our two-tailed test, which we're denoting by hypothesis type A. We have a left-tailed test, that is hypothesis type B, and then a right-tailed test, hypothesis type C. Now in this scenario, the test statistic that we'll use is the studentized test statistic rather than the standardized. All right, and so we're going to denote, in the context of this hypothesis test, we'll denote the studentized test statistic by lowercase t calc. All right, and it's calculated this way. So the difference, theta hat minus the hypothesized value of theta, which is theta 0, divided by the estimated standard deviation of the sampling distribution of the difference, which is represented in two ways: the square root of theta hat squared sub theta hat, and also by theta hat sub theta hat, or sigma hat sub theta hat. Now, under the assumption of normality of the estimator theta hat, the following rejection criteria provides hypothesis tests that have a significance level of a desired level of alpha. And so for the two-tailed test, we're going to reject the null hypothesis if our test statistic t-calc is either strictly less than negative t sub alpha over 2 comma df. So that's the negative of the upper alpha over 2 percentage point of the t-distribution with df degrees of freedom. Or if t-calc is greater, and I see that I have a typo there as well. All right, so I need to get rid of that, so that other criterion here would be to reject if t-calc is greater than the positive value t sub alpha over 2 comma df. So the upper alpha over 2 percentage point of the t-distribution with degrees of freedom equal to df. For a left-tailed test, hypothesis test B, we're going to reject the null hypothesis if t-calc is less than negative t sub alpha comma df. So the negative of the upper alpha percentage point of t-distribution with degrees of freedom equal to df. And then finally, for hypothesis test C, the right-tailed test, the rejection criterion is to reject the null hypothesis if the test statistic t-calc is greater than t sub alpha comma df. So if it's greater than the upper alpha percentage point of the t-distribution with the degrees of freedom equal to df. Now again, under the assumption of normality of the estimator theta hat, the following formulas give the p-value for each of the three types of hypothesis tests. So for the two-tailed test, the p-value is equal to 2 times the probability that a t-random variable with degrees of freedom equal to df is greater than or equal to the absolute value of t-calc, where again t-calc is the observed value of the test statistic. For the left-tailed test, hypothesis test B, the p-value for the test is the probability that a t-random variable with degrees of freedom equal to df, and I say I have another couple of typos here. I need to put df in the subscript of these two t's on B and C here. All right, but the p-value is the probability that the t-random variable from a distribution with degrees of freedom equal to df is less than or equal to the observed value of t-calc. And then finally, for the right-tailed test, hypothesis test C, the p-value is equal to the probability that a t-random variable with degrees of freedom equal to df is greater than or equal to the observed value of t-calc. Now again, as always, regardless of the type of hypothesis being tested, whether it's a two-tailed test, a left-tailed test, or a right-tailed test. When using the p-value to decide whether or not to reject the null hypothesis, the rule is to reject the null hypothesis if the p-value is less than or equal to the significance level being used for the test, which is alpha. Next, let's look at constructing confidence intervals for theta. And so we'll start by constructing a 1 minus alpha times 100% lower confidence limit for theta. And so again, let capital T sub theta hat denote the studentized version of theta hat. Then under the assumption of normality of theta hat, we have the following string of equal quantities here. So 1 minus alpha is equal to the probability that the standardized version of theta hat, so cap T sub theta hat, is no more than, less than or equal to, T sub alpha comma df, okay, where T sub alpha comma df, again, is the upper alpha percentage point of the T distribution with df degrees of freedom. We then replace the notation for the standardized version of theta hat by what it's equal to inside parentheses, and so theta hat minus theta all over theta sigma hat sub theta hat. And then if we manipulate things algebraically to get theta on all by itself, then we see here that we get the probability that theta is greater than or equal to theta hat minus T sub alpha comma df times sigma hat theta hat. Okay, so that probability, the probability that the parameter theta is greater than or equal to this random variable theta hat minus T sub alpha comma df times sigma hat sub theta hat, that probability is equal to 1 minus alpha. And so that implies that a 1 minus alpha times 100% lower confidence limit for theta is given by this quantity, theta hat minus the t-value times sigma hat sub theta hat. Next, we'll construct a 1 minus alpha times 100% upper confidence limit for theta. And so again, under the normality of theta hat, the assumption of the normality of theta hat, we see that using this sequence of equal quantities, we see that the probability that theta is no more than, it's less than or equal to, theta hat, and that should be a plus T times sigma hat sub theta hat. So I've got a typo there I'll need to fix. Okay, so we see that that probability is equal to 1 minus alpha. And so this implies that a 1 minus alpha times 100% upper confidence limit for theta is given by theta hat plus this t value times sigma hat sub theta hat. And then finally, if we combine lower and upper confidence limits, each at a significant or at a confidence level of 1 minus alpha over 2 times 100%, the resulting confidence interval is going to have a confidence level equal to 1 minus alpha times 100%. And so the lower confidence limit would be theta hat minus T sub alpha over 2 times sigma hat sub theta hat. And the upper confidence limit would be theta hat plus T sub alpha over 2 times sigma hat sub theta hat. And so summarizing these three types of confidence intervals on one slide, all right, we have three listed here. So a 1 minus alpha times 100% lower confidence limit for theta, a 1 minus alpha times 100% upper confidence limit for theta, and a 1 minus alpha times 100% two-sided confidence interval estimator of theta. Now we'll also have opportunity to use the squared studentized version of theta hat. And so let's take a look at this. And so it can be shown that the square of a studentized estimator, all right, and so we are squaring cap t sub theta hat, and that's equal to the square of the difference theta hat minus theta, and that squared difference divided by sigma hat squared sub theta hat. That random variable, which we're going to denote by cap f sub theta hat, it can be shown that random variable has an f distribution with one numerator degree of freedom and denominator degrees of freedom equal to df, where df is the number of degrees of freedom associated with the estimator sigma hat squared sub theta hat. And so this squared studentized estimator can also be used as a basis for making inferences about theta when the variance of theta hat, sigma squared sub theta hat, is unknown. Now, although all three types of hypothesis test about theta can be performed using the squared version, the squared studentized estimator of theta is usually used only when performing a two-sided test, so hypothesis test A. All right, and so the null hypothesis again would be that theta is equal to theta naught against the alternative that says that theta is not equal to theta naught, so this is this two-tailed test. The squared version of the test statistic will be called by fcalc, and it's equal to the square of the difference, theta hat minus the hypothesized value of theta, divided by sigma hat squared sub theta hat. And then for the rejection criteria, under the assumption of normality of the estimator theta hat, the following rejection criteria provides a two-sided hypothesis test possessing a significance level of alpha. And so again, for this two-sided test, hypothesis test of type A, we reject the null hypothesis if the test statistic fcalc is greater than the upper alpha percentage point of the F distribution with one numerator degree of freedom and denominator degrees of freedom equal to df. All right, so that's the end of this lecture video. We will continue on in the next lecture.